This video discusses AC circuits, transformers. Now, before we get into the actual transformers, I want to talk about transmission of electricity. And so transmission lines typically use ALSR for the wiring to transmit the electricity. So this AL stands for aluminum conductor, and then the SR means steel reinforced. So if you look in the center here, you can see that this is steel reinforced. You see the dark gray there is in the center is the steel wire for reinforcement, and then the electricity basically travels through the aluminum conductor. So remember, aluminum is a conductor that has twice as much resistance as copper, but it's cheap and it's relatively rigid for being used out in the weather. But it's not quite strong enough, so they put steel in the center. And if you remember with AC circuits, because of the as the frequency goes up, the current likes to travel near the edge. It's what they call the skin effect, and so therefore not too much of the current actually goes through the steel in the center. Alright, but this conductor, of course, has some resistance. Any conductor has resistance, and this having aluminum has much more than copper would. Okay, but what I want to do is I want to talk about, transmission lines and transmitting the energy, because when we transmit energy, you see here there's some transmission lines, right? But what happens is we transmit them at very high voltage. And so I want to kind of describe why that is, and then we'll come back to the transformer. So here is a case where we have a house. Okay, so in my house I actually have a 100 amp breaker in my house, and in that alright, so in my house I have a 100 amp breaker, and actually the other day I had a short, and it actually tripped out this 100 amp breaker. So that means that I had 100 amps flowing into my house. Now, to make the math easy, let's just say that we had 100 volts, right? Normally it's actually 120 or even 240, but let's just make it nice and easy and say we had 100 amps flowing through my box at 100 volts. So the resistance of my house, right? So the resistance that my house saw as the load would actually be, right, Ohm's law, 100 volts divided by 100 amps, which would mean that my house actually had a resistance of about 1 ohm. Okay, so I had about 1 ohm of resistance in my house at the time that breaker tripped. Okay, so when we can also then calculate how much power that was, right? So power is voltage times current, right? So power is voltage times current, and so that means that I was using see, power is voltage times current, right? So 100 volts times 100 amps gives me 10,000 watts, or 10 kilowatts. Okay, so at the instant that breaker tripped, I was at 10 kilowatts. Okay. So my house was actually drawing 10 kilowatts of power. All right. And so the question becomes then, what was the voltage that the energy company had to supply? What was the voltage E here that they had to supply? So if you think about, something like a Thevenin circuit, right? You're going to have a voltage, and then you have resistance. Okay, so we have resistance in the line. And so you're going to have this resistance here, and then you have your load resistor. So my house was the load resistor. But think about this, if the energy is being generated 100 miles from the house, okay, and so there's resistance all along this wire, right, all the way along. And so if at my house I have 100 volts, the question is, what is the voltage that must be supplied, okay, to and so because some of that voltage, of course, is going to be dropped here, right? So the voltage being dropped in the line, right, is the current I, which was 100 amps, times the resistance of that wire, okay? And 100 miles of wire, there's going to be quite a bit of resistance. All right, so remember, in my house I have 1 ohm of resistance. So let's see how much resistance is actually in the wire. Okay, now here is the ALSR form here for different types of wire. So I just to make it I just kind of selected the top one here. So this was 6 gauge, okay, American wire gauge, 6 gauge wire. It's got a code name of Turkey, don't really know why, but but if you look at this, this tells you for every 1,000 feet it has about 0.86 0.806 ohms, okay, 0.806 ohms for every 1,000 feet. Okay, so remember, in a single mile is over 5,000 feet, right? 5,280 feet. And I'm saying that, hey, we're transmitting this 100 miles. And so if we want to look at, all right, if you do the math here, okay, for 5,280 feet per mile, and every 1,000 feet it's 0.86 ohms, and we're going 100 miles, that turns out that the wire here, 100 miles of wire is going to be 425.57 ohms if I take it out to 5 digits. And remember, I just calculated that I had 1 ohm of resistance at my house. Okay, so if you look at that, then if I have 100 volts here at my house and I've got 100 amps going through there, that means the electric company over here has to generate 42,000, okay, 557 volts to get one, or actually that's how much, that's the voltage, sorry, that's the voltage that's being dropped across the wire. Okay, 42,000, okay, 557 volts are being dropped across the wire. And so the electric company means they've got to generate 42,657 so that I have 100 volts at my house. Okay, now this example is with no transformer. Okay, with no transformer. Okay, this is just straight voltage. The electric company, just to feed my house, 100 amps to my house, the electric company is going to have to generate over 42,000 volts. Okay, and remember, we already said before that my house is using 10 kilowatts. Okay, if I'm running 100 amps, that means it's 10 kilowatts of power to my house. So they're getting to my house, they're delivering to my house 10,000 watts of worth of electricity. But if you look over here, right, 42,000 times 100, okay, so that's going to be 4.27 megawatts. Okay, they're going to have to generate something like 4.27 megawatts to get 10,000 watts at my house through this 425 ohms of resistance. Okay, and that's just impossible. There's no way that the electric company could possibly, right, be generating over 4 million watts to get 10,000 watts to my home. Okay, if that was the case, we would not have electricity like we have it now, right? And of course, they would be charging me for 4 million watts, not 10 kilowatts. Okay, they would be charging me for megawatts. All right, so let's look and see what happens if we have a transformer. Now, this is assuming an ideal transformer. Okay, an ideal transformer means that there is no loss. All right, which means that the power in is equal to the power out. Okay, so if we look at this, right, we already said that at my house I'm using 10,000 watts, 10 kilowatts. Okay, that's what my house is using. So if we use a transformer and we step up, okay, so we're going to step up the voltage. So these guys over here have to generate a voltage so that on the power side, they're going to step up the voltage. So on the high side of the transformer, they're giving me 10,000 volts. Okay, now the way a transformer works is it uses the inductance. So we've talked about inductors before, but what they do is they use two inductors. All right, and so you get a certain number of turns on this side of the transformer, and then for every 100 turns on this side, I'm going to have one turn here if it's a 100 to 1 transformer. Now, you can wind it any way you want, but let's just say that I'm using a 100 to 1 turn transformer. Now remember, power in must equal power out. Okay, and so that's 10 kilowatts here on the right side, but I have 100 amps here, okay, and I have 100 volts. Right? So what happens when we put this through a transformer, it steps up the voltage, okay, and steps down the current, or vice versa, depending on which side that you look at. Because remember, the power needs to be 10 kilowatts. Okay, the power needs to be 10 kilowatts. And so if I step up the voltage here so that I have 10,000 volts, so if I have 10,000 volts here, then 1 amp gives me my 10 kilowatts. Right? 10,000 volts times 1 amp gives me 10 kilowatts, or 100 volts times 100 amps gives me 10 kilowatts. So the power is the same. But look at the difference now. If I step this up, that means over here on the left side, should probably move this over here to the left side. So on the left side, right on the left side of this transformer, on the left side of the right transformer here, I've got 10,000 volts, but I only have 1 amp. But on the right side over here, right over here on the right side, I've got 100 volts, but 100 amps. It's the exact same power. All right. However, look what happens now. See, before, if we went back up here and look at, so if we look at our previous calculation, right, to have 100 volts here at my house, they were supplying 42,000 volts, right, because they were supplying 100 amps. Okay, they're supplying 100 amps across 425, 426 ohms of resistance. So there's a voltage drop across there, right? 100 amps times 426 ohms is going to be 42,000, 42.6 basically volts being dropped across there, across this 425 ohms. See, we can't do anything about the resistance in this wire. All right, it just is what it is, so that we can get that much current. However, right now we only have 1 amp. Okay, we only have 1 amp flowing through this wire. This 100 miles of wire, we only have 1 amp, not 100 amps. So instead of us actually dropping dropping 42,000 volts, we're only dropping 426 volts. 1 amp times 426 ohms is 426 volts. So we're only losing 426 volts across there. Now I know that sounds like a lot, but remember that the voltage at my house is 10,000. Okay, on the left side of my house, this voltage here is 10,000. And so therefore, 426 compared to 10,000 now, that's not very much. That's just a fraction of 10,000 volts. All right. So then when we look at this side of the transformer here at the power company now, all right, it's at 1 amp. On the right side of this transformer, we have 1 amp. And so therefore, it's got to be supplying 10,426 volts, right? Because my house has 100 volts at it. We have 10,000 volts on this side. So here we're going to have 10,426 volts. But when we run that now through this transformer again and take it back down, we take the voltage down, we only have they only have to supply 104 volts. Okay, 104 volts to get me 100 volts at my house. Okay, so that is why we use transformers, and that's how we can transmit energy hundreds or even thousands of miles through wires that have a lot of resistance, right? 426 ohms, that's, when you consider that your house, if you're using 100 amps at your house, okay, and you have 100 volts coming in, then that is 1 ohm, right? Your house looks like 1 ohm to the power company. But the wire is 426 ohms, or even more than that if you're going further than 100 miles, right? But by stepping up the voltage, here so that your current drops, okay? So remember, your current right? If your power loss, there's resistance in here, right? And the power in there is I squared, right? Power is I squared R. So the power lost in your transmission lines is I squared R. So if you can drop your current by a factor of 100, right? I dropped my current from 100 amps down to 1 amp, then, okay, so that's a factor of 100 squared, right? So I've reduced my power loss by a factor of 10,000 by using a 100 to 1 turns ratio and stepping up my voltage from 100 volts to 10,000 volts. Okay? And so that is a very practical use of transformers, and that's why, you know, driving down the road you see power lines and you see these transformers, right? That's why we have to use them, because without the ability to step the voltage up, which steps the current down, we could not have electricity in our homes. All right, and so again, the key to this is the power in is equal to the power out. And so if you have 100 volts and 100 amps, and you're feeding that into a transformer that is 1 to 100, what that means is you're going to step up the voltage. So you're going to get 10,000 volts, 10,000 volts. So you're stepping up the voltage. The voltage is going up. That's what we call a step up. But the current goes down. So your current, you get down to 1 amp for your current. So if you step up the voltage, you step down the current the same amount, the same factor. All right, and that factor is what we call the turns ratio. Okay, so that factor is called the turns ratio. All right, so here's just some different pictures of some large power transmission transformers, right? And so you can see, right, a lot of big substations, they, you know, we're transmitting electricity hundreds or thousands of miles, we step up that voltage to very, very high voltages, right? So sometimes it's like 500,000 volts, okay, and even higher than that. Okay, then they kind of break it down into at smaller things. They drop it down like to 69,000 volts. Okay, so you know, and this would be like a transformer out on a pole near your home or something. But they step that voltage up to very, very high voltages. Now notice this is 340,000 volts is what this one. You know, this one over here is doing, and the example I did was only going up to 10,000 volts, right? So you know, you can do the math there and calculate how much less loss you would have by doing that and stepping it up to even higher voltages. Okay. All right, so when we talk about transformers, okay, again, a transformer is two inductors that share the same core. So we've talked about inductors, and we talked about how inductors store energy inside this magnetic core. However, if you have a transformer, it does not store the energy. What it does is it passes the energy through. As you push current through this coil, it doesn't store the energy in the magnetic field, but it transfers that energy through the magnetic core into the second coil. All right, and so you have what's called a primary coil and a secondary coil. All right, and a lot of times they'll put a dot on here, and the dot indicates polarity. So if you have your dot here, if the voltage is positive, then the dot shows you the polarity match, and it also kind of shows you the current. So if you have current coming in, so if we have current coming into the dot, into the primary, then the current is going to go out of the dot in the secondary. Okay, so your current is flowing into the dot on the one side of the transformer, out of the dot on the other. Now remember, for transformers to work, they basically need an AC voltage. Now they do have what they call like DC transformers, but they're actually they're turning on and off the DC voltage to pass this current. Okay, so you actually need some sort of alternating current for transformers to work. Okay, now another thing that we get into with transformers, okay, well, I already talked about the turns ratio, right? So you have your turns ratio. Normally they refer to it as like N to 1, right? So if you have like a 100 to 1, like we were talking about before. Right, so for instance, if you had a transformer that on the primary side you had, say, 50 turns, and on the secondary side you had 5 turns, okay, then this would be a 10 to 1 transformer. So it would be stepping down the voltage by a factor of 10, but the current would be stepped up. Okay. Now, inductors have what they call self-inductance. Okay, so they induce that energy into that magnetic field. But when you put the two coils there, that's when we get into what we call mutual inductance. So mutual inductance means that these two are sharing that magnetic field. So when energy is put into that core from one coil, then it's being induced into the second coil. Now, another nice thing about most transformers is that you have electrical isolation. So there's no current, no electricity flows through that core. So you have this secondary side is completely isolated from, electrically isolated from the primary side. Okay, so we have isolation. Now there are cases when they build a transformer and they tap the same coil for the secondary side. Okay, this is sometimes referred to as an auto transformer, and it does not have electrical isolation because these, you know, one side of that transformer is basically ground or electrically connected on both the primary and the secondary side. Okay, but if you know, like most, like the power company transformers and stuff, those actually all have an isolate. Those are all isolating so that their ground is isolated. Okay, and most like transformers that we use in our house, right? Because when you have 120 volts at your power outlets in your house, but you know, computers and various things like that use only maybe 12 volts or even less, 5 volts, something like that. And so they have transformers in them that step down the voltage even further. And those are typically isolating type of transformers. So they actually isolate your ground. Okay. Alright, so that's just kind of a quick little intro to transformers and why they're so useful.